So my project is about Borufka's algorithm. So first, this was developed by Otakar Borufka in 1926. He was a mathematician. There's a lot of sources that claim he was an engineer working for the electrical company in Moravia, which is part of the Czech Republic. However, he was a mathematician who knew people that worked there, and they asked him for help, saying, "How can we construct an electric power network that can connect all of Moravia in the cheapest way?" And that's how the first solution for the minimal spanning tree came out. Now, minimal spanning tree is one of the most known problems in graph theory, in computer science. This being the first solution, it was revolutionary. It is true that nowadays we use mostly like other algorithms, such as, for example, prims and crosscalls. But both of them, when they developed their own solution, they both quoted Borufka, saying he was the original author of the first solution. So the different principles of the algorithm. First of all, is a greedy algorithm. So that was something kind of recent in those ages. This was nearly 100 years ago. And what greedy algorithm means is going to look for the cheapest edge at each component without really taking into account the overall cost. Now, this can be a problem because it can potentially create a non-minimal spanning tree, which is not ideal. Then another really particular thing about this algorithm is that it allows for parallel implementation. Now, this is different from prims on crosscalls because the original one is they don't allow for this other option. However, there's been different iterations, not iteration, but different versions of the original algorithm that do allow now for parallel implementation. Now, one of the problems that this has is that it assumes that every node has different weights. Now, this makes sense knowing why it was made, thinking is to connect different cities. Well, different cities are going to have varying length. The possibilities that the difference from city A to B and A to C is the exact same thing, then is highly unlikely. And this works in an iterative way. So at the beginning, each node is thought as a separate tree, then it's going to find its cheapest edge to connect. It will connect them. If it did not create a cycle, it's added to what will be the final solution. Then different subtrees are merged together, and then you repeat those steps until the MST is found. Now, why is this algorithm so important? So the MST now is just, even though it's not exactly this algorithm, and as I said, they maybe use prims, crosscalls. The idea of MST is used in so many different industries. So anything that's kind of network design, different kind of design, where you had different cities or in electricity in a house, how can we get electricity throughout the whole house in the cheapest way? Then an MST is perfect for this. Currency market is looks like it's used to see the relationships between different currencies. The same thing happens in bioinformatics with genes, so they can transform a problem using the MST. It makes it easier because instead of it being a multidimensional clustering problem, it becomes a tree partitioning problem. This means that then each cluster is going to be a subtree of the MST, which is a simpler solution, is going to facilitate the implementation of the basic clustering algorithms because of the shape that you get.
Okay, so this is my Python code. So I have a structure in 3 different functions, one for plotting each step. Borufka is going to be the main one, and to find the index. So the main one is we have 2 empty lists, one for the MST where to store these different steps. It's going to sort them by the way, so we have consistent results. Each vertex is thought as its own component. It's one of the characteristics of main characteristics of the Borufka algorithm. These are the steps, so we can then plot them differently. It's going to find each index. If it's not found, it gives the index. If not, it'll give -8, just random, a negative number that's not going to clash with any kind of error. We'll do a check-in that they're not the same and they don't have the error here and here. I'm going to create a unique key and add to the cheapest edge if it is the cheapest edge. And then we want to merge the different components also from the Borufka algorithm. One of the main things that it has different subtrees, and then after getting the cheapest one, it will merge them together. Append the cheapest edge. This is for the steps as well. And then this is the functions for the plotting, which then if we run, I've set it as if they're different cities in the Czech Republic. We'll get, yes, perfect. So step number 1, start with different nodes and its weights. So it'll get the cheapest one, and then connect the different cities. So we have a shape where all of them are connected, and this would be our MST.